In this video, we introduce partial derivatives. Let's let f of xy be a real valued function of two variables x and y. The partial derivative of f with respect to x evaluated at the point xy is defined to be the limit as h goes to 0 of f of x plus h comma y minus f of xy over h, provided that the limit exists. So notice in this ratio, y is fixed and x is the first coordinate x changes from x to x plus h, and so the numerator is the change in the value of the function when we change the x coordinate by h units. So this is the change in f divided by the change in x. So this limit is the rate of is the instantaneous rate of change of f with respect to change in x. The partial derivative of f with respect to x is here denoted by denoted by f subscript x. The partial derivative of f with respect to y evaluated at xy is the limit as h goes to 0 of f of x comma y plus h minus f of xy divided by h, provided the limit exists. Now, this limit is the rate of change of f with respect to change in y. So again, fx, the partial derivative of f with respect to x evaluated at xy is the rate of change of f with respect to change in x, and the partial derivative of f with respect to y is the rate of change of f with respect to change in y. Let's do an example. Let f of xy be equal to the function be equal to x squared plus y squared. Then the fx of xy is equal to the limit as h goes to 0 of f of x plus h comma y minus f of xy divided by h. This is equal to the following limit. So here f of x plus h comma y is going to be x plus h squared plus y squared. So this is f of x plus h comma y, and f of xy is this. And now we expand the square x plus h square. So this would be x squared plus 2xh plus h squared plus y squared minus x squared minus y squared. After cancellation, we see that we only have two terms left in the numerator, 2xh plus h squared. And we can factor out h here. We get 2x plus h multiplied by h. Now then the h in the numerator cancels the h in the denominator. So we are left with 2x plus h. And as h goes to 0, then we end up with 2x. So we see that for the function f of xy equal to x squared plus y squared, the partial derivative of f with respect to x evaluated at xy is equal to 2x. Similarly, if we calculate the if we look at the partial derivative of f with respect to y, that's this limit where x is fixed and y changes from y to y plus h here. And again, we just plug in, we just evaluate f at x and y plus h. That's going to give me x squared plus y plus h squared. And this is f of xy. And then if I evaluate the limit the same way, we're going to end up with 2y. So the partial derivative of f with respect to y evaluated at xy would be 2y. one thing that I want you to observe here is that, so when we looked at the derivative of f with respect to x, here we got 2x, and when we looked at the derivative of f with respect to y, we got 2y. So notice that when I take the derivative of f with respect to x, if I assume that y is a fixed constant, then if I take the derivative of this with respect to x, then I would end up with 2x, because the derivative of a fixed constant would be 0. So when we take the partial derivative of f with respect to x, then think of y as a constant, and then take the derivative. Similarly, if I am taking the derivative, the partial derivative of f with respect to y, then assume that x is a fixed constant, and then take the derivative with respect to y. So notice that if you think of this term as being fixed, then the derivative of this quantity with respect to y would be 2y. Okay, so now I want to make a remark here. So I'm going to rewrite the partial derivative of f with respect to x. So recall that the partial derivative of f with respect to x is defined by this limit here. Now I'm going to rewrite this limit. So here I have f of x plus h comma y. I am going to rewrite that as that, so the input here, x plus h comma y, I'm going to rewrite that as x comma y plus h comma 0. So notice that if I add x, y, and h0, then I'm going to get x plus h comma y. So I can write x plus h comma y as xy plus h comma 0. Now then I'm going to rewrite h0 as h times 1, 0. And then finally I can rewrite this term as f of capital X comma h times the vector I. So you recall that I is the vector 1, 0. So that's a unit vector in the direction of the positive x-axis. And capital X is x comma y. So we can rewrite this limit as the limit as h goes to 0, f of capital X plus hi minus f of capital X over h, where capital X is xy. So basically my point here is that the limit as h goes to 0 of f of x plus h comma y minus f of xy over h can be written as the limit as h goes to 0, f of capital X plus hi minus f of capital X over h, where capital X is the same as the point xy. Now recall that this limit is the partial derivative of f with respect to x, so therefore the partial derivative of f with respect to x evaluated at capital X is equal to this limit, which is the limit as h goes to 0 of f of capital X plus hi minus f of x over h. Now similarly we can write the partial derivative of f with respect to y evaluated at capital X is the limit as h goes to 0 of f of capital X plus hi minus f of capital X. I have a typo here, so this should be j. So the partial derivative of f with respect to y evaluated at capital X is equal to the limit as h goes to 0 of f of x plus hj minus f of x divided by h. So So you can think of this limit here as the rate of change of f in the direction of the vector I. So let's examine this limit a little bit more. So if we are fixing the point x, and capital X has coordinate x and y. Notice that where is the point h times I for any h? Well, if you look at the orange line, that's a line parallel to the x-axis passing through x. And so x plus hi, so recall that I is a unit vector in the direction of the positive x-axis. So x plus hi would be a point on this orange line. So basically notice that we are changing the input capital X in the direction of I. So here is x and here is x plus hi, and then we are, so this in the numerator, then we have the change in f when we change the input from capital X to capital X plus hi, and in the denominator is how much change is made in the input in the direction of I. So this ratio, we can think of that as the rate of change of f as the input changes in the direction of I. So this is the rate of change of f in the direction of I. Similarly, we can think of the partial derivative of f with respect to y at x as the rate of change of f in the direction of j. So this time, notice that capital X is the same as before, but now x plus h times j, that's going to be a point on the vertical line passing through the point x. So we are changing the input in the direction of j here. Recall that j is a unit vector in the direction of the positive y-axis. So we are changing the input along the y-axis, that is in the direction of j. So then we can think of this as the rate of change of f in the direction of j. So in the case of the partial derivative of f with respect to x, notice that y is being fixed and the input is changing only in the first coordinate. And in the second case, when we are looking at the partial derivative of f with respect to y, x is being fixed, the first coordinate x is being fixed, and the second coordinate y is varying. Now, if I have the function f of xy, which is equal to 4 minus x squared minus 2y squared, then I want to find the partial derivative of f with respect to x evaluated at 1, 1. Now, the partial derivative of f with respect to x, what is that? Well, when I take the partial derivative of f with respect to x, I'm going to assume that y is fixed. So if y is a fixed constant, then 2y squared is also a fixed constant. So then the derivative would be the derivative of 4 with respect to x, which would be 0. Derivative of negative x squared would be negative 2x. And the derivative of negative 2y squared with respect to x would be 0, because again, with respect to x, so we are assuming that y is a fixed constant. So then the partial derivative of f with respect to x evaluated at 1, 1 is equal to negative 2. Similarly, the partial derivative of f with respect to y evaluated at xy would be negative 4y, because this time we're going to assume that x is a fixed constant, and then we get the derivative to be negative 4y, and the partial derivative of f with respect to y evaluated at 1, 1 is equal to negative 4. So when y evaluated negative 1, 1, then I replace y by 1. There are a bunch of other notations that we use for the partial derivatives. So instead of using fx, sometimes we use delta f over delta x to denote the partial derivative of f with respect to x. If we want to emphasize the input here, then we write delta f delta x, and we write xy within parentheses here. Sometimes we write dxf, so this is the derivative of f with respect to x, or sometimes we write d1f, and the reasoning behind writing 1 here is that you're taking the derivative of f with respect to the first coordinate x. Similarly, fy can be denoted by any one of these symbols here. So if I have the function f of xy is equal to x squared times y cubed, then what's the partial derivative of f with respect to x? Well, so we're taking the partial derivative of x squared y cubed with respect to x. Now when we do that, we are going to think of y as a fixed constant, so y cubed is a fixed constant. So the derivative here would be y cubed times the derivative of x squared with respect to x, which would be 2x, so we get 2x y cubed. Similarly, what's the partial derivative of f with respect to y? In that case, we're going to think of x squared being a fixed constant factor here, so we get x squared times 3y squared, so we get 3x squared y squared. So that's the partial with respect to y. More on notation, if we denote f of xy by z, then we can also denote the partial derivative of f with respect to x by zx, or delta z over delta x. Similarly for the partial derivative of f with respect to y. Let's look at the function f of xy is equal to sine of xy. The partial derivative of f with respect to y evaluated at 3 comma pi over 4, okay, so what's the partial derivative of f with respect to y? Well, when we take the derivative with respect to y, we assume that x is a fixed constant factor here. So then think of x as like imagine that x is like a c, a constant. Well, then the derivative would be cosine of xy multiplied by the derivative of xy with respect to y, and the derivative of xy with respect to y would be x. Again, thinking of x as a fixed constant. So we get x cosine of xy. Now we evaluate that at 3 comma pi over 4, so x is 3, y is pi over 4. So we get 3 times cosine 3 pi over 4, and that's the same as 3 times negative root 2 over 2, which is equal to negative 3 root 2 over 2 at the end. Okay, so I'll stop the video here, and I will see you in the next one.